Hello, everyone. Thanks for joining the Temporal Graph Reading Group today. Today we have Farimah here presenting our joint work last year at Europe's dataset and benchmark track towards better evaluation for dynamic link prediction. So a few words on Farimah for people who are not familiar. So I've been working with Farimah for a few years now, and she is a postdoc now at McGill University and Mila, supervised by Professor Rehane Rebane, and she conducts research on dynamic graph neural networks and temporal graphs. She completed her PhD at McGill University in computer engineering. During her PhD, she was working on anomaly detection on cryptocurrency transaction networks. She also served as the reviewing chair in the Temporal Graph Learning Workshop, which was at Europe's 2022. So we're great to have her as speaker today, and excited to share this work with you all. And feel free to ask any questions while the presentation is going on. I will hand the mic to you.
Yes, thanks everyone for joining. Today I will talk about our paper, which was accepted in NeurIPS 2022 on the dataset and benchmark tracks. As Andy mentioned, this is a joint work with Andy and Kelly under the supervision of Rehane. So the title of the work is Towards Better Evaluation for Dynamic Link Prediction. So I will start with giving an overview about the evaluation strategies for dynamic link prediction. Here we have dynamic graphs. So an important component of this kind of data is that they are temporal, and the graph structure or the graph characteristic will evolve over time. So in the currently used strategies, we have a temporal split of the data. We chronologically split the data into train, validation, and test set, train the models on the training data, and then test it on the test set, which is some information from the future of the model. One thing that is interesting in this domain is that the link prediction mostly is modeled as a binary classification. So we have the positive edges, which are given in the data set. They are the actual edges of the graph, and they constitute the positive instances. However, we should have some kind of negative instances that let us compare the performance. And the common practice is that we randomly sample the negative edges from all possible perf nodes. So there are also some common metrics that are used for the dynamic link prediction performance. One of them is area under the ROC curve, and the other one is the area under the precision recall curve or average precision. And one interesting observation is that most of the state-of-the-art methods, as we have seen during the previous reading group talks, they can achieve a very high and close to perfect performance on this task. So if we take a look at the current data set that are available, we can see that most of the data set comes from a limited domain diversity. By that, I mean, we have a lot of data set coming from social networks or interaction networks, and just a few of the data set are from different networks. And we can see that the current state of the art can achieve very high performance on these data sets. Specifically on the Reddit data set, we can have more than a 94% AUROC for dynamic link prediction task. And this is not just for one model, this is for many different state-of-the-art models that can achieve very high performance. So with that being said, the contribution of our work was had three main components. The first component was that we saw that there is a limitation on the domain diversity, so we wanted to have a more diverse data set. And in that regard, we propose 6 new dynamic graph dataset that they come from different domains than the social networks. And for better understanding of the dynamic graphs, we also propose 2 new visualization techniques that help us to understand the evolution of the dynamic graphs in a better way. In addition, we also closely investigate the negative sampling impact on the evaluation of different methods. And we propose 2 novel negative sampling strategy, which are aware of the recurrence pattern of the dynamic graph. And finally, we take a look at a very simple but strong baseline for dynamic link prediction, and show that although the proposed baseline is simple, but it can achieve high performance for this task. So let's start with the dynamic graph dataset that we focused on. As I mentioned, we had proposed like 6 new datasets that they came from different domains like transport, politics, economics, and proximity. And these datasets show different characteristics. So they have diverse properties and graph distribution comparing to the previously existing dataset. Before getting into knowing the dataset in detail, I just wanted to give some categorization of the edges in the dynamic graph. As I mentioned, in this type of work, we split the data chronologically. For example, if we consider that we have a time t, which split the training and the test data, then the edges can be categorized considering this specific time. So if we have, we consider that we can have some edges that we are only seeing them during the training. We can have some edges that we see them during the training, but due to the recurrence pattern of the dynamic graphs, they will reoccur at the test time. And we consider to call them as transductive edges. And we also can have some edges that we only see them during the test. And we call these edges like inductive edges because we don't have any historical information about them. So having in mind in this definition, we propose 2 new visualization technique and some indices for better understanding the dynamics of the dynamic graph networks. So first, we propose the temporal edge appearance plots. These plots actually show the ratio of the repeated and new edges at each of the timestamp. For example, here we have the t-plots for the Reddit dataset. We can see that on the x-axis, we have different timestamp of edge appearance, and on the y-axis, we show the number of edges that are repeating from the previous timestamp versus the number of edges that are new at this current timestamp. And this vertical line specifies the time split where we splitted the data into training and test set. One thing that is interesting is that we can see there is a high variance in temporal evolutionary pattern of the data set. And these metrics can give us some notion about the ratio of the edges that are repeating over time. Based on these plots, we defined the novelty index. It shows the average number of edges that are new at each timestamp to the total number of edges at that timestamp. So here we had the t-plot for the Reddit dataset. We also presented the t-plots for other datasets. And here you can see that we have indicated the novelty index in the parentheses for each dataset. One thing that is interesting is that the dataset that come from similar domain, like for example, Canadian Parliament and US Legislative, which are from the political domain, they have some similarity in terms of the t-plots. And we can see that novelty gives us an estimation of the portion of the positive edges that a pure memorization-based approach cannot predict correctly. I will talk about it in more details later, but if you can imagine that we have a method that only memorize what it has seen previously and make prediction based on those information, then if a dataset has a high novelty, then this method cannot achieve very good performance. So one other thing that is interesting is that some data set like the social evolution, like this one, they mainly comprise of repeated or reoccurred edges, while others such as mock data set, they have a high ratio of the new edges. So this plot actually helps us to show the significant differences in when edges occur and the distinction between the new data set that we propose with the previously existing data set. For example, we have proposed the flight data set, which has significantly more unique edges and higher number of edges per timestamp comparing to other data sets. In addition to the T-plots, we also wanted to show how consistent the edges are repeating over time. And for that purpose, we proposed the TED plot, which shows the temporal edge traffic. In this plot, we have the percentage of the observed edges on the x-axis, and on the time axis, on the y-axis, we show at which time those edges have been repeated. So for generating these plots, we have sorted the edges based on their first time that they have appeared, and with the edges that appeared on the same time, we sort them based on the last time that they appear. So we can see that edges can, the edges that lasted, that had the first last time they appeared first. So these plots, they show the recurrence pattern of the edges over time, and based on these plots, we defined two indices. The first one is the recurrence, which shows the ratio of the edges that we see during the training and test time to the total number of edges in the training set. So it is actually, if we consider these plots, it shows the ratio of the orange edges to the total number of edges in the training set. And also the other index that we defined is the surprise index, which shows the edges that we only see during the training, during the test to the total number of edges that we see during the test. But by that, I mean the ratio of the red edges to the total number of edges that we see during the test. Here, the horizontal line specifies the time split where we split the data set into a training and test set. Again, for the Reddit data set, we have recorded the recurrence and surprise indices here. And for the other data set, we have these two indices in the parentheses for other data set. Similar to the previous index, recurrence and surprise also is diverse for different data set, but we can see that there are some similarity between the data set from the same domain. One thing that is interesting about the TED plot is that they provide more insight about the edges that are used for training and testing of different dynamic graph models. Again, if we consider a memorization-based approach, it can potentially predict the transductive positive edges because they have been observed and they have been recorded during the training. And in particular, if these edges appear consistently, then the memorization-based approach is likely to be very successful. And this is when the reoccurrence index is high and the surprise index is low. And on the other hand, if the edges appear at some point in time, but they don't reoccur, then the memory is likely still helpful, but simple and full memorization cannot work well. And the reason is that it will result in incorrectly predicting those edges that are not reoccurring as being still existent. And this is the situation where the reoccurrence index is low. And finally, memorization is not helpful at all for predicting inductive positive test edges at their first appearance time, because these are the new edges that they haven't been observed before. And this is the situation where the surprise index is high. So that was all about the dataset aspect. Now let's take a look at the negative edge sampling and its impact on the evaluation of the dynamic link prediction. I will start by taking a look at the random negative sampling, which is the currently common strategy for selecting the negative edges. So as I mentioned, the link prediction task is mainly modeled as a binary classification problem. We have the set of positive instances as the actual edges that are being observed, but the negative sampling is needed for training or evaluation of the models. The standard negative sampling works in the way that it samples the negative edges from all possible pair of nodes. One thing that is actually problematic here is that this kind of sampling, although it is it's the common way that we sample the negative edges even in the static setting, it's not aware of the recurrence pattern of the edges. So it's not very well defined for the dynamic link prediction task. The other problem is that currently the state of the art, they don't actually check the collision for the positive versus negative, but that is like a minor problem because it can be solved very easily. So considering that this was the random negative sampling strategy, we proposed the historical negative sampling. The goal is to have some notion of the recurrence pattern of the edges. So here we want to sample the negative edges from the set of edges that have been observed during the previous timestamp, but they are absent in the current timestamp. So there should be negative edges. So one thing that is interesting in this negative sampling approach is that it considers the recurrence pattern of the edges. And the edges come from the set of edges that we've seen during the training, but they are not present in the current timestamp. So this kind of negative sampling based on the historical edges, it provides harder negative samples because the model cannot rely on just memorizing what it had seen previously. We also take a step further and propose the inductive negative sampling. Here, we consider the recurrence pattern of the edges that have been seen during the test time. So again, we are focusing on the historical edges that are not repeating, but those historical edges come from the test set itself. So we are sampling from the set of edges that have been observed during the previous timestamp of the test phase, but they're absent in the current timestamp. And by that, it will hinders the model to just rely on memorizing what it had seen during the previous timestamp of the edges. And also it will help the models to see how they can adapt to the new edges that are only visible during the test set. So in this plot, we have actually showed the impact of negative sampling. And we can see that if we use different kind of negative sampling, namely historical and inductive negative sampling, because the negative samples are harder than the standard setting, then the different methods can achieve different ranking. And it's interesting also to notice that the performance of all methods will considerably decrease when we choose harder negatives. Apart from the negative sampling impact, we also wanted to discuss a baseline for dynamic link prediction. So here we propose a very simple memorization baseline, which we call it EdgeBank. And the intuition behind EdgeBank comes from the T and TET plot. From the T and TET plot, we inferred that there are many edges that occur over time. And we're thinking that does the memorizing observed edges work well or not? So here, EdgeBank is a pure memorization-based approach. It can detect edges with frequent recurrence pattern. For example, if we consider that we have like 3 different edges with 3 different timestamps in the memory, then at each timestamp, if we query one of the edges, if that edge exists in the memory, then EdgeBank will return true. But if that edge doesn't exist in the memory, then EdgeBank will return false. So it is purely based on memorization of the historical interaction of the network. There are two scenarios where EdgeBank fail. It is the first scenario is that we are making prediction for a negative edge that has been previously seen. For example, if we consider that edges between S1 and D1 is a negative edge at the current timestamp, then EdgeBank will return true because it had this edge in the memory, but it is not a positive edge at the current timestamp. The second scenario is making prediction for unseen positive edges, exactly like the example that we have here. For example, S1, S5, and D8, it is not present in the memory, so EdgeBank cannot predict this edge correctly. So for the memory update policy of the EdgeBank, we consider two different variations. For the EdgeBank Infinity, we store all observed edges in the memory, so it can remember the edge. It can remember edges from a long time ago. However, it is prone to false positive because if the edges don't repeat, then they will result in wrong prediction. We also had the EdgeBank TW, which remember edges from a fixed time window from the immediate past. We set the time window equal to the duration of the validation split. And here the focus is on the edges that have been seen in the short-term past. In this plot, we compared the performance of EdgeBank with the other state-of-the-art methods. We can see that EdgeBank can achieve very competitive performance, particularly in the standard setting, and that shows how much different methods are relying on the memorization approach. And one thing that is interesting is that EdgeBank TW is actually the state-of-the-art in the it's actually the second best performing method in the historical setting. So now I will switch to the experimental result that we had. First, I wanted to mention that we consider recent models that have achieved very high performance for as our baseline, like the CAW, TGN, TGAT, DIREP, and JODI. And in this plot, we can see the performance of different models on different data set, comparing to the performance of the EdgeBank with two different variations. So one thing that is interesting is that the performance of the models on the new dataset that we have proposed are different from the performance of the models on the previously existing dataset. And we can see an inconsistency in ranking among methods across the different dataset. Another interesting insight is that we can see the memorization baseline are on par with the state-of-the-art methods. However, they don't require learning or hyperparameter tuning. So we can see that with a very simple baseline, we can still achieve high performance. And these were results for the random negative sampling. We have the same set of experiments while the negatives were sampled by the historical negative sampling. Here we can see EdgeBank TW is the state-of-the-art in many data sets, and it can achieve still a considerably high performance. But EdgeBank Infinity doesn't reach good result, but it was expected because it is recording everything that it has seen, and it doesn't update its memory. The same result for the inductive negative sampling shows that when the negative edges are selected from the inductive historical edges, then EdgeBank is not expected to work well, and that is actually it was expected because it is not a method that updates or learns something. It's just memorizing the previously seen edges. Here we show the impact of negative sampling strategy across all the methods. So we can see that there is a clear drop in performance between the negative sampling strategies. and the ranking of the models will change when the negative samples are selected from the harder negatives. And here, finally, we wanted to show how correlated is the performance of one model with the memorization. So on the left-hand side, we had the correlation of each model performance with that of the EdgeBank Infinity as a pure memorization approach. And on the right-hand side, we had the performance loss when we switch the standard negative sampling to historical or inductive negative sampling. And we can see that the performance of EdgeBank Infinity correlates with the performance loss of methods when harder negative samples were selected during the evaluation. And one thing that this plot infers is the idea of whether the state-of-the-art methods really go beyond just memorizing the history of the edges or not. With that being said, actually, I want to somehow sum up what I just explained. The contribution of the work was, in fact, like threefolded. We added 3 new domains and 6 new data sets, and we provide novel visualization techniques to show the diversity and recurrence pattern of the edges in the dynamic graphs. We introduced new negative sampling strategy and show that the ranking of the method and their performance will change when different or harder negative samples are tested during the evaluation. And we show that if we consider the recurrence pattern of the edges, then we can select harder or more difficult negative samples. And finally, we show that a powerful but simple baseline method like EdgeBank, which only works based on the memorization, can achieve very high performance. And we wanted to further investigate whether there is a way that we can go beyond the memorization and actually learn what is happening on the edge reoccurrence or first occurrence of the edges. So thank you everyone for listening. Here are some resources. We have the paper and its GitHub project. And also we had the code as a pip install. And if you have any question or idea, feel free to reach out to me or Andy. And I would be happy to take any question.
Yeah, thanks for the nice presentation, Farimah. And yeah, feel free to ask any questions. So usually I would ask a ton of questions, but this time I have no questions. So yeah, so feel free to go ahead.
I actually have a question on the evaluation. So you have those repeated edges and you have the new edges, right? And did you do an evaluation for the different methods, just looking at how good they are for the repeated edges versus how good they are for the new edges? So which method is better for new edges, for example?
Yes, actually, we don't have such separate evaluation in this work, but I can say that, for example, for the historical negative sampling, the negatives actually are just from the repeated edges. So that's actually one thing that we consider for future work, just to divide the set of all edges, positive and negatives, into recurring and new edges. But one thing that it is not very clear in this figure, but the negative edges are just repeating negatives. Sorry, they are selected from the edges that we have seen, but they are not repeating. So they are somehow like historical negatives. So we have a history of the negative edges, but they are not something that the model have never seen.
Yeah, I understand. Thanks for explaining. Is there some kind of correlation between what method is good and at certain data sets and this novelty index for the data sets?
we can probably make some kind of those kind of intuition. We haven't targeted it yet, but we can see that, for example, if a data set has a very high novelty, for example, the mark, then in the inductive setting, I think it will achieve very low performance because there are a lot of new edges. We had some discussion on in the paper, but I can't. Yeah, actually, we can see that even we have very high novelty, then the performance of the even random negative sampling is low in the for this data set.
And also the performance of EdgeBank is relatively low.
Yes. Yeah.
Okay.
So although we are not reporting it, but there are some intuition, there are some correlation between those indices that we have defined with the actual performance of the models, because they are somehow reporting some notion about the difficulty of the data set.
Yes, go ahead, Farimah.
First, thanks for the presentation. Very interesting, and I like that you're coming with a very simple baseline to show that these very complicated methods are not necessarily doing so much better. I wanted to ask, well, first, have you thought of modifying this EdgeBank to have, to say, be a bit smarter, but still based on memorization? I'm thinking you could have somehow used the number of times edges have been repeated in the past, how long ago, this type of things. Like you still wouldn't have had to train and still, yeah, and it would have still been like completely like, or not necessarily deterministic. You could add a bit of randomness to it, but maybe it would have improved even more. Or is it something that you want to do further?
Yes, actually, that's one of the future plan that we have considered. Although, as you mentioned, the EdgeBank is very simple, but it can achieve good performance. But if we can somehow make it better by having a very small component that is learning what is happening on the network, definitely it can achieve better performance. So here we have just two different memory update policy. But as one of our future work was to somehow help the EdgeBank learn about what is happening on the graph.
Yeah, but so where it wouldn't, like, I'm thinking if you have an inductive setting where you're having new nodes or even new graphs or something like this, do you see a way of adapting like, do you see a way of still constructing a rather simple baseline?
Yeah, that's a very good question, because all of the experiment that we have here was for the transductive setting, so we don't see any new node. But yes, and that's one of the reason that we have just tested for the transductive setting, because EdgeBank at this level cannot predict anything good for the new nodes. But if we equip this EdgeBank with a notion of learning something about the graph, then definitely it can have some performance for the inductive setting as well.
Thinking. Yes. Okay. Thank you.
Thank you.
I do actually have other question if nobody else wants.
Yeah, sure.
I very much like this TED plot. I'm working with knowledge graphs where you have different types of edges. And I was thinking if there's any way how we could modify this or extend these TED plots to be able to deal with different types of relations or different types of edges. So I was thinking one way might be to just have this differentiation if the same edge has existed between two nodes or not, or to have something like one plot per relation type, maybe. But I'm not sure. Does anybody else have another idea what we could do to incorporate different relation types? probably too much information for one plot.
Yes, actually, as you were explaining, I was thinking that maybe if the number of relations are limited, we can have one TET plot per relation. But one other thing is maybe we can use different color for different relation at the same, I mean, with the same intuition here. For example, if we, instead of just having orange color for any edges, we can have different color for each relation. But it would still be much complicated.
Yeah, it depends a bit on the data set. If there are like 5 relations, I think that's fine. If there's like 200 relations, it's gonna be a mess.
Yeah.
I have to think of that because I really love those plots. 2 different types. Roxana, what do you think?
Yeah, so I was just thinking you could, it depends like how you want to count the edges. If you count the edges just based on the source node and the target node, which is basically what's being done here, and you kind of like disregard the relation, that's something you can look at. But then you could have different plots that are like a variation of it, where each triple is a relation. And then maybe it's interesting to observe that as well. And of course, if you have a limited number of relations, then you can do it per relation. If you have a lot of relations, that's going to be hard.
Yeah, I think that sounds reasonable.
Or maybe having, I mean, extending 2-dimension to 3-dimension so that the third dimension consider the relation. But again, if the relation are limited, that would make sense. But
yeah. Thanks for the you have the script to create those plots on your repo, right?
Yes, yeah. Everything is on the GitHub repository of the project.
Cool. Thanks.
No problem.
Yeah, maybe we can have some. So it would be nice, but I'm not sure how easy to run the code it is. But I think it should be pretty straightforward. But it would be nice to have some sort of online tool or automatic tool that you just put a CSV file that will give you these plots, right? Just preliminary check for a new data set you plan to work on. That would be cool. But of course, that requires a bit more coding than just having a function. Yeah, and then of course, there's could be like other plots that shows, like I think looking at plots of a temporal graph is generally quite informative for just understanding the data set. So I feel like a lot of time it's just when you want to do something on temporal graph, you first need to see what's actually in the data set, and sometimes it's not like not very trivial. Like even just basic plots, like number of edges over time, and these kind of things are like generally very helpful to understand the data set and their differences. Yeah, and I guess like another thing is like the density. So we don't have like density over time, but also that's another plot I think is pretty interesting, and they can vary a lot across domains. Yeah, and I think with the data sets that we provided here, it's not just for method purposes where you just want to test on data set, but also you can kind of do different comparisons across domains and so on, and potentially add new data set to it and so on. Yeah. Okay. Yeah. Thanks for the presentation, and thanks for all the questions. Yeah. So if there are no more questions, we can wrap up a little bit early today as well. And then feel free to send us any question you have on Slack and through email or whatever channel you prefer. Yeah. So essentially, I think the baseline we propose is really straightforward, and it's most scalable because it's literally just O of E. Well, E is like number of edges. It's literally reading the data set once, and you have it. So, and then you just need to store it in you don't need a GPU, of course. It's just a hash table. So, so I would say like try it out and then see the results for yourselves when you are playing with new method. And I think this could be interesting to see how EdgeBank can work for like knowledge graphs, right? In your case, like Julia. So so how do you have this? So you can just have like tons of dictionary, one for each type of edges. Or maybe there's something more to be done there. And I'm not familiar with temporal knowledge graph literature, but yeah, but I think we'll be learning more in the incoming talks as well. So, okay, sounds good, everyone. So so let's wrap up for today, and yeah, have a nice week.
Thank you.
See you all next week.
Thank you. Bye-bye.
Thanks for